Welcome back to the day's proceedings. So I'll basically, for the rest of the session, I will give a very brief description of a sort of HTK implementation of the subspace-based modeling approach here. Then Mohit Agarwal will talk about some issues with UBM, training Gaussian mixtures for UBMs. And then Nagendra Goel and Sam and Pinar will talk about pronunciation modeling. And then Dan will finish up. Okay? So I'll go quite briefly here. Basically, I had a similar implementation of the joint subspace modeling system. We were calling it subspace Gaussian mixture modeling, which unfortunately overlaps with Herb Gish's segmental GMMs, and we apologize for that out front. So let it be.
I apologize. Just do so much better that people
forget all about Herb who, right? So basically, I evaluated on the Wall Street Journal task, which is a bit different. We're talking about 100,000 Gaussians instead of, I guess, 10 or 15,000 Gaussians for the call home systems. And the baseline word accuracy here is on the order of 5 or 6%, and so it's a different task. And
hopefully the error rate.
Did I say accuracy? What I meant was the error rate is much lower. So anyway, just to keep showing you the model over and over again, the probability density for a given HMM state is given in terms of a model space component, which is describing the phonetic variability with these shared substate projection matrices and weight and state specific, shared model space model space projection matrices and state specific weight vectors, and a combination of that and the speaker space model. And then the parameterization has sort of been enhanced to include the notion of substates. So I'll quickly describe the training procedure, and I don't know if anybody has really done that so much. And the important point in this slide is the fact that when we initialize these systems, we're initializing them from a baseline HMM model, a traditional parameterized HMM model. And we, the system starts out here from the occupancy probabilities for given states and mixtures. And basically, since these state-dependent weight vectors in modeling phonetic variability, the labeling they have to assign an observation to a given state or a given phonetic category derives from those posterior occupancy probabilities. So the training procedure starts by having our initial baseline HMM. We define the states, the state tying and everything based on that HMM, and that stays fixed through the procedure. Assume we've trained a pool of full covariance Gaussian mixtures, and in our case we randomly initialize these subspace vectors. That's not what's done in the system that Petter described. Anyway, so we initialize with this stuff. We come up with these initial probabilistic alignments, and then we basically use the EM algorithm to iteratively train the weights and the subspace parameters of the model subspace system, and we basically will iterate on that, use that model to obtain a new set of occupancy probability, and so on. So it's fairly straightforward and fits in nicely, I think, in anybody who's created a software for training traditional HMM parameters finds that this fits in the sort of standard EM framework in a reasonable way. Yes?
When you say decode, should I read a line?
Yes, you should read a line. My mistake. Sorry about that.
No, decode is fine.
Yeah. Yeah, but it's not clear. Anybody else have spite bugs in my graph? Okay.
20 bucks?
What?
20 bucks?
20 bucks? No, we don't pay for finding my mistakes. So we basically in all of these things we iterate on pay attention on estimating the model space parameters. In our implementation, we're not estimating the weights here, and that's just an omission, something we didn't get around to. Which is something that is being done in the system that Petter described, and as in their system, we're just increasing the number of substates by randomly perturbing these weight vectors. Okay, then having trained these model parameters, we hold them fixed and train the subspace, the speaker subspace, and parameters, and during adaptation, we estimate these speaker vectors. Okay. Right. Do I have the update equations on slides? Sorry?
I'm going to show them later.
But maybe Dan does. Okay, sorry. You always want to get to the math, I guess. So the Wall Street Journal task is established. It's been people have been working on it for 15 years, I think. The thing that distinguishes it from Call Home again is it's I think the vocabulary size is actually similar, but it's vastly more training data. I think there's a factor of 5 more hours of training speech. There's about 1,000 speakers. The baseline system that we use to initialize with and to compute baseline performance has 6,000 states and about 100,000 Gaussians. The baseline performance for this 5K bigram language model is over 5%, and I think that's pretty consistent. The other thing that's characteristic of the Wall Street Journal system is it is close talking, microphone, quiet conditions. So it turns out that VTLN and regression-based adaptation techniques don't improve on this baseline very much. So the thing so we have about 8 million parameters in the baseline system, and we've configured these things in basically the only different configurations we looked was increasing the number of substates. We started with 256 Gaussians and a subspace dimension corresponding to be the same as the feature space dimension, and we increased the number of substates from 1 to 4. What we found is I could not quite reach the baseline word error rate here. I got to about 7.3% word error rate. We think that's largely, I think with tuning, we could probably make it. But yeah, I think I thought it was perhaps an interesting task because it's very difficult to improve on the baseline using any of the sort of standard techniques, adaptation or speaker or feature space normalization techniques. But on the other hand, this is a pretty well established task, and it's hard to, with the amount of training data you have, to improve on that baseline with any statistical significance.
Just to
Yeah.
speculate, given that you have 80 hours of acoustic training data, I wonder whether you don't have enough Gaussians in your UVM.
I think I would defer to Petter's results there, where, you know, over a broad range of trade-offs between shared parameters and parameters assigned to states, things turn. It's not that sensitive. They, for example, had a result where they had 1,000 UBMs and 1,000 Gaussians as compared to 200 Gaussians, and just by assigning additional substates, the state-specific subspace, they sort of made up for the difference. Is that a fair characterization? So I'm.
Issues of the weights, not updating the weights.
Oh, I see. That's right. You said you don't update the weights.
Because that doesn't work really with that.
Okay. That's.
Yeah, no, I had forgotten that. You did say that.
Right. I got too many things. Right, so I'm not updating this, and that I'm sure has an effect. But, right.
But then you are not updating it because that's too difficult or time consuming?
Because we hadn't gotten to it.
Pardon?
Because we hadn't gotten to
Oh,
it.
I see.
Yeah. Right. It turns out, well, yeah, so. Okay. So anyway, the other thing, I was up late. We thought we would be able to, so we've gotten within 15% of the Wall Street Journal baseline. We assumed that additional tuning should make up that difference. We had been more optimistic about the subspace-based speaker adaptation, and that did not have an effect. I mean, I think we got something like 0.2% absolute improvement, and that's really not statistically significant. And you know, and we don't know why. Likelihoods improve in training, and word error rate does not. And so we've had on the same corpus had some success with this. This should say speaker space adaptation, and so that was a surprise. But we think it's a bug. So for us, the post-workshop work, we want to sort of, this is an HTK-based implementation that fits fairly nicely in HTK. We made some shortcuts which break other things that we'd like to fix. And so there's nothing about this parameterization that requires any very special framework. And I think that's the point. And we'd like to evaluate these techniques on other tasks. I promise I'd keep it really short. So this is my last chance to thank all my colleagues here. We'd like to thank people at Cambridge for the HTK. Thank the guys at BUT for use of their cluster, and all the gang here, and my colleagues back at McGill, and thank you to our host here at CLSP.
I'm going to discuss a comparative approach for the various approaches of initialization of UBM ASR. So, Universal Background Model is a full covariance trained GMM that covers all speech dates on a trained Gaussian. Before training, we must initialize it with trained Gaussians of a baseline system. So I have investigated various ways of doing this. So starting from a to start with, we can start with a flat training, that is choosing global means and variances with all Gaussians having equal weights, or we can have a baseline HMM set. From a baseline, but this approach is better and the most optimal. And the global means and variances can be used for calculation of variance flows that can be used while re-estimation. From the baseline HMM set, which contains approximate 20,000 frames, 20,000 Gaussians, sorry, and we can get to 100 Gaussians through agglomerative clustering or through random selection. Clustering based on the which two clusters have minimum change in likelihood, and after we obtain 100 Gaussians, we'll follow an approach for variance initialization, then we'll send it to the training module. While doing variance initialization, we'll scale variances, we'll calculate the variance flows, and while doing training, we will firstly train the diagonal covariance GMM, then we'll train the full covariance GMM instead of directly training the full covariance GMM. The advantage of using this, we have a lesser number of parameters and much lesser trade-off.
Should we be interested in scaling variances? What is this?
Yeah, I'm just scaling the variance vector with a factor of 1.5.
It's just an ad hoc thing to get more widely distributed counts so you don't go look at minimum. It's not super fun.
These are the results. Maximum likelihood per frame versus iterations on the 3 experiments that I performed. Firstly, the random that I have shown in that block diagram. Firstly, the random selection of Gaussians. Second, the clustered selection of Gaussian. Thirdly, the clustered Gaussians with scale variances and following some experiments on variance initialization. So we see that the scale variances seems to work. We have a much greater likelihood, but there is a general conception that all three different approaches for the initialization models seems to have a similar likelihoods. So we may conclude that the proper initialization of variance is important, but since all initialization techniques had similar effect on likelihood, so we must be careful while choosing likelihood as a measure of quality. Also, we need to evaluate this model in the whole ASR system. Thank you.
Okay, so I would like to switch gears here a little, and we have had a wonderful afternoon with the UBMs, but another promise made for the workshop was that we are going to reduce costs on everything. So we have something which can be trained with 1 hour of data, and you get a reasonable acoustic model for recognition, but still one remaining part of the system is the lexicon. So here I present some efforts on that direction. So in a nutshell, the speech recognition system has 3 important inputs, or let's say 4. One is the extraction of features which come from the acoustics, and then there is a pre-trained acoustic model, and there is a language model, and typically a handmade lexicon or a pronunciation dictionary. And all of these combine to give you the final output. Over here, the lexicon is a representation of the phonetics. It's essentially like a lookup table. So here cat has the phonetics of KAT, and ran has a different set of phonetic symbols, and that kind of combine to string together your models which are used for recognition. Now, if we look at the cost of developing a recognizer in a new language, of course, the biggest cost is transcribing the audio data, and then there is this cost of getting text for language modeling, and the third cost factor is the pronunciation lexicon. And one problem in that, especially for languages which are not very widely used, is that qualified phoneticians are very expensive and very hard to find, and even if you find someone, they make mistakes.
I don't
And
think they'll agree that they make mistakes. I think they'll agree that they
right. We do need a large lexicon. For example, for call home English, the OOV rate is right about 5% for a 5K lexicon, and it reduces to 0.4% as we go to a 62K lexicon. So the approach we take here is that we would try to guess the pronunciation from the limited lexicon and the audio that we have. So in principle, ideally, we would just like to maximize this likelihood function, which is the probability of the audio features given the pronunciation. One problem is that we cannot directly get to this likelihood because there are words in the, if we are starting with a lexicon of only 1,000 words, for example, and we have recorded audio and transcripts which cover, let's say, 5,000 words, then there are other 4,000 words for which we don't know what the lexicon entries look like. So we cannot start evaluating this function right off the bat. And a obvious implication of this kind of objective function is that every time I see a new occurrence of a particular word, I could potentially choose a different pronunciation for that. But typically, multiple pronunciations have not helped in improving the performance of the system. So this objective function needs a lot of regularization. And we were searching for a good way of doing that. And one possibility was to tie up the grapheme to phoneme generator with the lexicon selection. So G2P or grapheme to phoneme is a way of guessing the pronunciation given only the orthography of the word. So in this particular example, there is we see that A maps to this particular phoneme, and the 2T is mapped to this phoneme, and we call these units as graphonemes. And so here is an example of a graphoneme which consists of 5 graphemes resulting in 3 phonemes. And I would like to call Pinar to explain more details of this lexicon generation process.
So we have this iterative process for training these lexicons we have. We first start with an initial set of graphone probabilities, and then we use these probabilities to realign graphones with phones on the training data. So for instance, we have orders for each model that we have. For instance, this is up to the 4th iteration, the 4th model, because we have the mapping of 4 graphemes to a number of phonemes. It doesn't have to be like, there can be 1-to-1 mapping, or 2 letters, 2 graphemes can be mapped to only 1 phoneme, or 1 or more graphemes can be mapped to silence. This doesn't depend on anything. And after we get these probabilities, we re-estimate graphone probabilities from the alignments, and we continue this process iteratively until we reach the best results. So for the training process, we have an initial pronunciation dictionary, and we train this using the algorithm that I just described with G2P, and we come up with a model for predicting phonemes from graphemes. And afterwards, we use this model to predict the phoneme sequences of out-of-vocabulary words using G2P training iteratively over and over again. For instance, for English, you can see that the percentage error on the vertical axis is decreasing as we iterate the models and increase the context size of the graphones. From more than 90% error, we get around 15% error for strings. And you can take it from here.
So now we move to this regularized expression where we would calculate the probability of a pronunciation given the word, given our G2P model, and then constrain ourselves to those particular pronunciations which are most likely while maximizing our likelihood. And we, for the sake of convenience of implementation, we approximate this as argmax of x over the top 5 pronunciations. So the whole process of training, iterative training here, is that start with a handmade dictionary which is potentially very small, train a grapheme to phoneme, generate some pronunciations first, train an acoustic model, then force align using multiple pronunciations, create a new dictionary with the selected pronunciations, and reiterate your training process. Now, another alternate experiment would be that we could do a free phonetic recognition of the audio and match that up with the word level transcripts and pick up the most likely pronunciations. One advantage we could think of is, for example, in New York accent, everybody says X, and the orthography is ASK. Probably G2P may not be able to guess, and this kind of approach might allow us to break out of those typical mispronunciations. So this would be one additional experiment, and
Isn't that the same as force aligning with didn't understand what you described.
This one?
No, the next slide.
Right.
The blue boxes.
So here we use a phonotactic language model. So which is not the same as forced alignment, because it's free to recognize any phoneme sequence. And it is not limited to the restricted 5 pronunciations that came from the G2P. So,
it's an open phoneme loop. So you actually do
yeah, it's an open phoneme loop.
Decoding just set of words.
Right, it's decoding, it's not forced alignment.
But you have to match it somehow with a fourth line word. Otherwise, you don't know which.
Right, we need to know the starting point and the ending point of the word, for which we need to force align the word in a separate way, or do a decode. And we could try different approaches that way also. We did whatever we had time
Your
to.
assumption is that even if you don't have the right pronunciation, at least you get somehow the word boundaries. Correct.
So you're doing the alignment on the recognition output, the phone recognition output?
Yes. Alignment of the with the word boundaries with the phone recognition output. So essentially we are taking the centers of the phones and checking the word boundary and putting them into a bin.
Because unless you've gone to some extraordinary lengths in building a good phone recognizer, more than half your phones will be in error.
Right. So we really have to prune out a lot of garbage and try to pick up only the top candidates.
That's different, that's true.
So another idea that we would be exploring is unsupervised learning of the lexicon, where we have a lot of acoustic data for which we don't have the transcripts, and if we can use that somehow to add some additional words to our pronunciation dictionary. So what we do here is that we create lattices essentially to get confidence scores on the words and their starting and ending times. We also force align that data with this recognition output and make it choose from multiple pronunciations. And from that, we choose the high confidence words and introduce new pronunciations to the system. So at this time, I would like to invite Samuel to present various recognition experiments, and we can conclude.
So someone just gave us the 1,000 most frequently occurring words and their pronunciations. And now the goal is, given these 1,000 most frequently occurring words and their pronunciations, how do you start recognizing of the map? So that's what happens here. So you're given 1,000 most frequently occurring words of training data. And then what you want to do is you want to guess the remaining 4K of the training data. And you have a LM vocabulary size of 62K, so you have to guess that as well. So you have a whole challenge of guessing out nearly 60K of other words from just this 1K. And then the whole idea is, how do we use the loop that Nagendra was proposing and refine ourselves to come to the baseline number? Okay, so we start with the 100 most frequently occurring words. We have their pronunciations, and then we train G2P on it. Now, once you have trained G2P, just as what Pinar was saying, you can use the remaining of the training data, the 4K for which we need to guess, and the words that are part of your LM, and then you use G2P to guess out your dictionary. So that's the basic bootstrapping dictionary that you're going to use to start your recognition process. We also create a multiple pronunciation dictionary. I'll come in a minute for why we use that. Okay, so once we have these things in place, we can use this dictionary, which is a really guessed up dictionary. Only 1,000 words are within the scope, the rest are all guessed up. And then we go ahead and train our acoustic model. So we take the dictionary, we train the acoustic models, and we get a trained acoustic model. We use the test data, and then we get recognition. So this is our first bootstrap model using just 1,000 words in place. Now what we do is, since we have created a multiple pronunciation dictionary out here, we can use our audio data to tell us the best pronunciation from the set of multiple pronunciations that you have to sort of improve on your guessing. So what you do is you take your training data and use the crude multiple pronunciation dictionary that G2P gave in the very first step. So if you take the first 5 best pronunciations, probably the third or the fourth or the second, some of them would be the best thing that the acoustic likes. So you use your training data, use the multiple pronunciations from the previous iteration of G2P, and then you try to force align with the acoustic models. So in sense, we are trying to improve on the pronunciation that the acoustic model would like. And then you come up with the best pronunciation for the training words. So now we have sort of moved on from the problem of just having 1,000 words that we had to cover for your entire training data using this best pronunciation. So we have sort of covered up some ground in terms of the training data. Yes, please.
Do you use the context index?
I'm sorry, we use the monophones to do it. Yes, yes. Right. So that's what I was saying out here. So we use the multiple pronunciation and we get the best pronunciation for the training data, and then we retrain our G2P. So our G2P has sort of now is in a more better state because for at least the training data, it has been able to pick up the best pronunciations from the whole set, and then we are improving on what G2P would learn. So use G2P again to train up in a more better way, and then you use the words that are in LM that covers the test data to generate your dictionary, and then you use the acoustic models and you go ahead. So that's the loop that happens. So you keep doing this loop. So the output that comes out of here, the acoustic models, you use these acoustic models, do a force alignment again, find the best pronunciation. The attempt is to tune so that at least your training data has best picked up the best pronunciations that are there. So you start with your handmade phone set and dictionary, you train G2P with the dictionary, you train your acoustic models, you force align with the multiple pronunciation, you create a new dictionary, and then you keep doing the loop till you somehow start converging. Yes, please.
The 1,000 most frequent words that
Yes.
you start with?
Yes.
What percentage of the training data does it cover in terms of time?
In terms of time, I have not
Or
really
in
checked.
terms of tokens?
I have not checked that out. But these are so we have the remaining 4K remaining with us. So it's about 1/5 of it.
Switchboard, I think the top 100 words cover about 50%.
50%.
Yeah.
So 1,000 words could cover 80%?
Well, I don't know, but yeah.
Well, we haven't checked that number exactly.
Something like, well,
Yeah, that's something that we should probably check out.
Big switchboard is unique.
All right. Okay, so we do this magic loop of keeping G2P busy with new pronunciation. So to give you some feel of what's happening here. So if you had the full dictionary that comes with Core Home, no one given by Core Home itself, your baseline number is 44.35. Now if you train an acoustic model on that and then made sure that you had only 5K of manual lexicon. So remember, you don't have anything for your training data or for the vocabulary that the training data was looking for. It drops to 40.53. Now, if you had just the 1,000 words,
using G2P here.
right. So we guess the remaining part of it with G2P, and then you get to 40% over here. Now, if you had just the 1,000 words and you guessed all the remaining of it, and then you went for a decode, it drops to the 37.58. So we get to that bad state of affairs just because we don't have the correct pronunciations for each of the words. And now what we do is we go into the loop that I was describing before. We bootstrap our models, and then we keep going the loop where we try to improve our pronunciation. So what happens is we move from the first iteration gives me 39, then we move to 41, and then we move to 42. Now what we did in this experiment is that when we started the experiment, we constrained ourselves not only in the terms of the number of words that we had, but we also used the training data for 6 hours. So what happens is the 6 hours do not contain partial words, which is what Core Home has in a great amount. So what we did is we kept that apart so we don't want to confuse our G2P system with the partial words also coming in. So what we did in the last stage is that we pushed in back the whole entire training data into the loop and then went ahead again. And so what happens is the number goes up from 42 to 43.54. So the bottom line is by doing this iterative training process and with just 1,000 words in your hand, pronunciations of 1,000 words, you sort of come close to your baseline number of 44.35. You are short of 1%, but still you've been able to compensate for what we have lost.
Just a question.
Sure.
What same language model used everywhere?
Right. We didn't change the language model as well. Yeah. Right.
You also did not change the acoustic model, or?
Oh, the acoustic model gets changed in each iteration.
Okay.
In each
Also
iteration.
context clues and
Right. So the force alignment changes so that you get a best alignment again. Multiple pronunciation changes again so that you keep refining.
Sometimes the
Yes.
44.35, the first number,
Yes.
is that with 6 hours or 15 hours of training?
So this is with 6 hours.
Okay.
Yes.
So 44.35 should really be only compared with 42.1.
Right, but actually the
Actually, what happens is that adding that partial burst data somehow does not improve the performance much. So even the 15-hour data results are almost the same. I think there is a minor difference of 0.1 or 0.2.
So 44.3 will just become
44, 0.6 or something like that. It doesn't change much. You remember these are just the partial words, short partial words, things that are thrown out. They're not full sentences or sort of that. It's just the partial word fragments that are thrown off.
No, I didn't understand. I thought that you did not train at all on any sentence that contained a partial word.
Right, till this point.
So in other words, everything but the last line has 6 hours of acoustic.
Right. And then for the last loop.
If you go to 15 hours, the very top line with the full dictionary,
Yes.
you're saying between 6 and 15 hours, there's no big difference.
There's no big difference for call home. Yes. Right. Okay, so that's what we were doing with the loop in G2P. Now, coming to the second idea that Nagendra was saying. So what you can also do is you can go and find out databases for which you don't have transcriptions, but you have the audio data with you, for example, the switchboard data. And then you could use the acoustic models that you have here to create lattices, force align with them and create pronunciation. So you're sort of introducing new words and their pronunciations as well. But you're using the acoustic models that have been trained in this loop. So you have a constrained acoustic model, but you're trying to see if you can bring in new guys so that your G2P could somehow figure out what to do in the next iteration. And then you introduce these new pronunciations back into the loop, hoping that G2P would learn something new and then improve on that. But unfortunately, the numbers are not that convincing with that loop in place. So what happens is with the 6 hours of training data and you take in the switchboard data, what happens is your 42.1 number improves to 42.33. When we use the 15 hours, we had jumped to 43.56, and then if we do an unsupervised along with that again to see if we can improve our G2P, it almost remains the same. We couldn't get much gains. But we do see about 10K words coming in with multiple pronunciations, but the G2P is not able to learn out anything new from that. So the best number that we have is 43.56, which is short of 1% of the baseline. Okay, thank you.
One thing I want to point out about this last slide here is that this was with 6 hours of data, and unluckily when we jumped to 15 hours of data, we ended up using this as our starting point to bootstrap the next system. So it's not clear to us at this time that was it the first iteration of unsupervised which gave us this jump to 43.56, if that played any role or not. So we need to go back and redo this experiment in a clean environment where we use this as our starting point as opposed to that for getting this number. But yeah, it's not clear at this point whether unsupervised lexical training without any unsupervised acoustic model training is helping or not. But if we do both lexicon and acoustic training in unsupervised manner, that is yet another experiment to be done, which we believe will definitely help. Now, with Spanish, we had another set of problems, which I believe is important, that we start with very good acoustics. If you listen to the Spanish call home, people are speaking, the audio channel quality is as good as English call home, so there is no bad channel effect or anything, and they are not trying to cheat the system and try to speak extremely worse manner as opposed to English. Yeah, these are both difficult data sets, but still the English performance is about 13% better than Spanish performance. On the other hand, if that's the word error rate, about 13% better. But if we look at the phone recognition accuracy, Spanish phone...
Sorry, 31 is also the accuracy, right?
31 is the accuracy, right?
Spanish
which is 13% lower than English. But if you look at the phone recognition accuracies, Spanish is actually quite good. It's not a bad acoustic model for recognizing phones. And LM perplexity, yeah, we didn't have as much data, but it's still not terribly bad. We are in 127 range. So we want to ask the question that can we do something about pronunciations for Spanish? And here we are not starting with a very small dictionary, but this path of training the G2P and iterating on that is kind of ruled out because Spanish turns out to be extremely graphemic language in terms of pronunciations. So the G2P after you go to a model 2 is never really confused, and the error rate is.
Where did the handmade pronunciations come from?
Somebody wrote them down. LDC. Is that your question?
Yeah, well, I mean, I think in our system we just ignore pronunciations and just use straight letter to sound pronunciation.
Right. Well, we use something
That's
which
what I was wondering is if there was a hidden.
we use something which came from LDC, but I don't know where LDC got them from. Maybe they used letter to sound.
There was some suspicion that the lexicon that we have in Spanish might have been generated by G2P.
Yeah.
Because the error rate we got was awfully low. And I think Senti pointed.
I was going to ask you if you verified where that came from.
I verified that it's LDC.
No,
But
look at the notes in the catalog, they'll probably tell you.
Or just do a little proscript and see if the pronunciations match the spellings. That's really what I wanted to
well, they don't exactly match the spelling. There is some like model 2 covers it all. You don't need anything more than a model 2, but it's not exactly mapping from 1 to 1. So we are kind of out of this option, and we are out of unsupervised option as well because we did not have additional unseen data handy with us at the time of this workshop. So we ended up trying this third route, which is free phonetic recognition, match with the word level transcripts, pick the pronunciations, and try to plug them into the system. And when we do that and train our G2P on the new system, this is the string level accuracies we get. The top blue line here is the accuracy on the dev data, which is tainted by the extra pronunciations we picked up from our iterative system. And the eval data comes from a held out unseen data which came from the LDC lexicon. So if we zoom into this graph a little, we see that performance on eval is much better than the performance on dev. Actually, this was 50 test points, so 2 means that there was just 1 error. But on the dev, there were several errors because probably it picked up pronunciations from outside which did not match with the formula description. So when we did this experiment, the performance dropped from 31 to 30.7. So it's not very clear to us where this path is taking us. Maybe we added too many pronunciations. We added about 250 in a single shot. Maybe we should do it a little slow next time and add maybe 10 or 15 alternates every time and see where the pruning threshold should be.
Sorry to interrupt. I just looked it up. It says this is about the LDC Spanish lexicon. Except for the class exceptions noted above, pronunciations given in the field 3 of the lexicon have been generated automatically from the orthography using the following software and accompanying files. Blah, blah, blah.
That proves the point, I guess. So yeah, we are really trying to break out of that, and probably we try to break out too fast here. And if we choose a slower breaking out point and do a little bit more pruning of bad choices, we might end up getting some improvements here, and we might end up learning a little more about the pronunciations. We tried to measure against English, but again, the baseline that we were measuring against was tainted with some unsupervised lexical training as well. So it's not clear again whether the loss is because we started with a much better baseline, or because we did not prune enough.
Sorry, did you check out if you generate actually homophones or something like that, or?
Excuse me?
Let's try to keep it going because we're about half an hour behind schedule.
Okay, so all I would like to point out that the log likelihood of the data increases when we modify our lexicon. It's just that the accuracy doesn't increase, which probably points to that we are not pruning enough. And I would let Dan summarize for.
Slides. Now you can just finish your slides quickly.
Well, you are going to speak it anyway, so. By the way, I forgot about this one. We did another experiment where we said that we would keep all the 62,000 words that we know for English and just see if we can add a few more pronunciations to improve the lexicon. And we used G2P to generate a whole lot of alternates and did a forced alignment to add those alternates to our system. That affected about 250 pronunciations. Our baseline was 44.3 something, which improved to 45 if we use this method, using the whole lexicon that we have, but just augment a few more pronunciations. Now, if we introduce the concept of multiple pronunciations for the new pronunciations we added with pronunciation probabilities and all that, that had a very little impact, just increasing it by another 0.01 to 45.02. So in summary, G2P based iterative training method helped us achieve accuracies which are very close to the baseline system, starting with a very small lexicon. And we need to study the pruning and the adaptation schemes of unsupervised lexicon learning and phonetic recognition based learning a little bit more in detail so that we can merge those into our baseline system.
I just want to say something quickly before my prepared remarks, because I don't want people to be left with the impression that this stuff is not ready for prime time. Now, this is just a couple of this is just a couple of tables from a paper that this is a paper that's associated with the Gale program. You know, this Arabic and Chinese recognition and translation program. I just wanted to mention that IBM's submission to the latest Gale eval used this stuff. So obviously this wasn't some kind of fake baseline, because when Tony Tether is saying we're going to cut off your funding.
Which stuff?
The subspace GMM model.
Because we were just hearing about the lexicon.
Oh yeah, I'm sorry. So now, this is on 1,000 hours of data, and the baseline. It doesn't. These numbers don't say what the baseline was, but so these are the baseline numbers. It like has everything possible in it. It's like a really big language model. It has VTLN, constrained MLLR. It has some extra thing that we did, variable frame rate. So it has model space and feature space discriminative training. You know, we threw everything at it. And we're able to get better than this, not vastly better. The improvements here like 0.5, 0.4, 0.2. And on Mandarin it was working less well. It was like 0, 0.3, minus 0.2. So here there was almost no change. But you know, you don't really expect a technology that someone's been working on, you know, just for a few months to be, you know, that much better than something that people have tuned for years. And the improvements were much larger on one second. The improvements were much larger. This is just a setup that we used for debugging scripts. It was quite well tuned though. The baseline here, a fully adapted baseline. Sorry, this is the baseline number. This is it's 50 hours of broadcast news. I forget what the eval was. Some standard, NIST thing. And this is our baseline. This is the subspace model.
Right there, RTO4.
Okay, RTO4. And this is with discriminative training. Now you can do discriminative training on the subspace model. Like we haven't described how, but so there's about 20% relative improvement here, and I guess it's a lot less here. It's maybe between 5 and 10% relative, but it's still worthwhile. So let me go quickly through my previously prepared comments. Now the first thing, there's all this math, and some of you, namely Damianos, have been clamoring for the math. So I'm not going to go through it in the detail that I was going to go through it. And some of this has already been covered. So I'm just going to quickly flick through this. So this is the equations that people have been showing. I prepared some slides which kind of highlight bits of these equations and show you what it is. So J is the speech class. Typically there's like 5,000 of these. It's the phone in context. This is just a pretty standard equation for a Gaussian mixture model with a couple of special things. One is each mixture for each J has the same number of Gaussians in it, and there's this one-to-one correspondence thing. Another thing is that the variances are all the same. Like they don't vary with the state; they do vary with the I, with the Gaussian index.
So this is where in the UVM you once got your variance and states.
Well, I mean, you kind of train the within-class variances separately because they're different, but they're shared. So, and as the others mentioned, the means and the weights are determined by these special formulas in the subspace. And we have these state-specific vectors that describe how the states vary. So, and I think it's been made quite clear already that you have these globally shared parameters, and then you have these. And then you have the state-specific parameters. Now, there's this linear mapping from the state-specific parameters to the means, and the mapping of the weights is kind of linear in log space with renormalization. So you can kind of view it as linear in a kind of meaningful space. As we've mentioned, there's a correspondence between the Gaussians, between states. So Gaussian 1 is always Gaussian 1. It's not completely arbitrary. So we mentioned the UBM. This is just your kind of generic Gaussian mixture model. It's not really part of the model per se, but it is used for things like pruning and initialization. So it's kind of part of the scheme. So no one's really mentioned about the issue of the likelihood evaluation given this scheme. You can do some special tricks. Now you don't ever want to explicitly construct all of these vast numbers of Gaussians because it becomes completely unmanageable in terms of memory. But you can actually do it very efficiently doing the appropriate kind of pre-computing certain quantities on every frame. You can, basically it comes down to a dot product for each Gaussian in the final model. And you don't have to compute all of those dot products because you can do pre-pruning using the UBM. So my understanding in our current setup is that this SGMM-based model is faster than the baseline to decode with. I don't know how highly tuned the baseline was, but it's fast. Especially in decoding. In training, it's a little bit slower simply because there's very few states that you evaluate per frame, and these pre-computations begin to dominate. But it's not something that is a big problem. So now before you build your model, you have to have some kind of previously trained system. This is true of most conventional approaches for building systems. You usually will align with some previous system. This is not a big deal. You need a context tree that tells the mapping from your phones in context to your states. This is standard. And you need a trained UBM. There's various ways you can get that. It's not really a big deal. So you want to initialize your model in a sensible way. This is the way that we've been using. There's many ways you can do it. You can use PCA, you can use random initialization and iterate. But this is a reasonable thing. So you set the dimension of these vectors Vj, that is the dimension of your subspace, to be the same as the feature dimension plus 1, for instance 40. And then you set each of these V vectors to, on the first iteration, to just be a unit vector with a 1 in the first dimension. And the reason for that 1 is that you want, on the first iteration, you want the projected means to correspond to the means in your UBM, just so that you have reasonable alignments to start with. So to do that, you set each mi to just, the first row is like mu, the mean of the corresponding Gaussian in the UBM, and then you've just got the unit matrix, so that your V is then interpreted as an offset. So on the first iteration, when you estimate V, you're effectively just shifting the whole thing. And that's just a reasonable initialization simply because you expect it to converge faster if you do it like that than if you were to just initialize the V's or the M's to be random. Because then you anticipate having to do many more iterations. And then again, we set the W's to 0 vector so that all the weights would be equal on the first iteration. And then basically the model training, the others have mentioned, it's an EM process. Each iteration you pick a parameter type and optimize it. And you're guaranteed to increase the likelihood on each iteration. In fact, that's a slight simplification. We can combine some of the parameter types. And most of the time we can combine them all. But some of this is not justified by theory. So this is the auxiliary function that you get for the vectors. I'm not going to explain what that is, because it would take too long. But so it's a simple quadratic function. There's this linear term, the quadratic term. Now, these G and H, they can be computed from statistics that you gather from the data. You could, in principle, compute them directly from the data, but it wouldn't be the most efficient way to do it. Now, saying that it's a quadratic auxiliary function is actually, for the V's, it's a slight approximation. The most important term, which comes from the means, is naturally quadratic. But there's this term involving the weights that you kind of have to do a few approximations to make it quadratic. And there's no problems here with convergence or anything. It converges fine. So the update equation for V, you have this H and this G, and it's a very simple thing. You invert H and multiply by G. There is a slight wrinkle here in that H is not, mathematically speaking, H is always positive definite, but for practical reasons it can be singular. So you have to come up with some way of solving this, and I'm going to mention this later. With M, it's basically a similar thing, but the equations are a little bit longer. It's also a quadratic function, and here there's no hand waving. It really is quadratic. So this is the within class variance. This is some stats that you get from the data. This is derived from some statistics. It's kind of like an outer product of those vectors weighted by certain occupation counts. So the update is just, again, an inversion and a multiplication. But this time it's all matrices. Now, we have the same issue with this. This might not always be invertible, so then you'd have a problem. Before I mention the issue of invertibility, I just want to say briefly about the W's. These are the weight projection vectors that determine the mapping from the subspace to the weights. And the training these is just a little bit tricky. It's a very nasty nonlinear function that you're optimizing, and there's no natural auxiliary function that would, guarantee to maximize it. But you can make some approximations and come up with a quadratic auxiliary function that's quite easy to optimize. And once you formulate it in the right way, it's possible to find an update that's quite stable. So now this issue of non-invertible matrices. This is something that it's kind of in search of a clean solution. Now, like I say, these matrices can sometimes have 0 eigenvalues, and that corresponds to the case where there are certain directions that you can move the parameters that would not affect the auxiliary function. Now, this typically arises because these quadratic, these matrices are outer products of sums of vectors, and when not enough of those vectors have non-zero weight, you can get 0 eigenvalues. Basically, if you have an outer product of fewer things than your subspace dimension, it can become singular. So there's a couple of ways that you can fix this. Now, one way that I've done before is you can introduce a prior over the parameters. Like if the prior is some kind of nice conjugate prior that's just a quadratic function of the, in log terms, it's a quadratic function of the parameters. You can just kind of add that onto your auxiliary function and it'll work quite well. There's another whole approach that you can use based on, they have this notion of a least squares solution to a problem, which means that if there's a whole class of solutions to a problem because the problem is ill-posed or whatever they call it, you can just take the solution in that class that has the least squared value. So there's issues with actually implementing this because the statistics are in the form of these matrices that they're singular, but you can never really exactly determine the rank of a matrix, like how many zero eigenvalues it has, because you can never really distinguish between a zero value and a very, very tiny value. But there's ways you can solve this for all practical purposes. And it basically involves flooring very small eigenvalues.
So you can linear interpolate with the unit matrix?
Yeah, you could definitely do that. I mean, that's almost equivalent to the flooring, except it would have a very small effect on the higher eigenvalues. And also, you can just not update those parameters where you identify a problem, and that actually sometimes seems to work a little bit better. So, I think this is a whole area for further research because my understanding is this whole same issue arose in speaker ID, that Patrick Kenny, with his approach, he had these same issues of non-invertible matrices. And he kind of added this whole kind of Bayesian structure onto his things where you're integrating over some parameters, and then when you estimate the other parameter, you kind of use the distribution over the first parameter, and that stops these matrices from becoming singular. Personally, I'm not attracted to that approach because I think what you'd really like to do is use a nice prior that's well estimated. I haven't had a lot of luck doing that, but in principle, I think that's the way to go. Anyway, this is an area for further research. So Arnab especially has mentioned some of these extra things you can do on top of the basic model. We have the substates, we have the speaker subspace, we have the constrained MLR. I'm not going to go through these slides because they've been well covered. I want to talk just about the typical setup and tuning issues. So a normal setup, both if you have the speaker subspace and if you have the phonetic subspace, the dimension would be in the range 40 to 60. That's what I've found and what we found generally to be the best. You'd have about 400 to 1,000 Gaussians in the UBM. That's the number I. That's the number of Gaussians in each substate. And you have a number of substates that would typically be somewhat less than the number of Gaussians in a well-tuned baseline system. And if it's about half the number, that would be of the order of about a quarter of the number of parameters in your baseline. And we had an issue on our setup that none of the adaptation stuff, even constrained MLR, seemed to work when you estimated the speak adaptation parameters on silence as well as speech. And that was true even of the standard approach, CMLR. So I actually have a slide about this next, so I'm not going to belabor this point. One interesting feature of the tuning is that the language model weight always wants to be smaller than it would normally be. So my interpretation of this is that somehow these models are smoother or closer to real probabilities. Like my feeling is for normal Gaussians, when you get very far away from the center, you get these very extreme probability ratios. And perhaps we need to kind of scale down the probabilities to handle that. And perhaps there's something about this model that makes that not happen to quite such an extent. Okay, so I just want to talk about our difficulties with adaptation. The adaptation hasn't really been working quite as well as we would have hoped, and not as well as it worked for me in IBM. So now my setup in IBM, the speaker vector adaptation doesn't need a lot of data. There's just 40 or 50 parameters to estimate. So I would typically do it per segment. But the segments in broadcast news are not quite the same thing as the segments in conversational speech. Most of the segments in this call home is just yeah. So it didn't seem to work so well. We've been doing it mostly per speaker here. And
It's fair to do it on a whole conversation.
yeah, of course. I mean, of course, it's fair. I just got better results previously doing it per utterance. It was just working better. So yeah, we had this issue with the silence frames. It didn't work. I don't recall having this issue in IBM, although I think we may have done that by default. There seems to be something slightly weird about our silence model in this setup. We're getting a lot of like floored covariance matrices. I mean, they're full matrices, but we do kind of limit the condition of the...
I don't know, but the Colholm and Spitford, they have artificial silence patterns at the beginning sometimes.
Really?
Really zero lines.
Really? Well, it could be that. Maybe we can have a look.
Well, that may be the explanation.
Maybe.
The problem with silence.
Well, we'll have to have a look at that. So, yeah. So I mean, I hope it's an issue that is simple as that. Either that, or there's something about the model that makes it susceptible to these kinds of problems. I mean, this is again something for further research. I'm sure there's tons of things you can do once you identify the problem. I'm not going to go through this slide. This is just some issues of like how it's a more complicated model, so you need to think carefully about debugging and unit tests and stuff. So I actually have a separate stack of slides for the summary, and I hope. Okay, we're 7 minutes over, so if we do this in 5 minutes, well, it won't be deadly. So this is just to summarize kind of what we've done. This was just a slide about the initial objectives and like why we're here. So on the SGMM side, so I had done these experiments at IBM where I was getting a lot of improvement with this model on reasonably small data sets, and even getting some improvement on very large corpora. And well, I mean, my idea was partly just to popularize it, because sometimes these things take a while to catch on, and you know, if it's hands-on, that's a good thing. And also to do some more experiments on like multilingual situations, and what happens if you have very small training data. And on the lexicon side, Nagendra in his kind of day job had experience with the difficulties just the practical difficulties that people encounter when building stuff on new languages. Like, you don't have a good lexicon, it's very expensive to get one. We just need some kind of practical solution that will just reduce that cost. So these two projects were merged under, we felt there was some kind of common theme of these things work well with limited data. And that's worked out pretty well, actually, because the call home setup has been very convenient for both of us to work on. We also plan to do some kind of open source thing, and I'll explain what has happened with that. So, just to summarize what I feel that we've got out of the SGMM stuff, I think we've demonstrated that it works better than the baseline. I know Rick's stuff isn't working yet, but I'm confident that once the weights are added, it's going to work. We've worked on some new techniques, like this constrained MLR stuff is new. And we've kind of got a little bit more experience with like these issues with non-invertible matrices. I wasn't really actually getting that in IBM, and I think that was because I never worked with such a small data set. So, you know, I've realized the need to find a good solution to this issue, because it is kind of inherent in the scheme, but it's solvable. And also, I filled out all the derivations, which I'd never really done before. There's this, like, it's now 28 pages long, the document. I don't want to give the impression that it's because it's complicated. Most of that's appendices of stuff that are optional. And, you know. So, the multilingual, what I think is unique about our experiments on multilingual is that we actually got an improvement, because most of the time when people publish on multilingual setups, they have some totally catastrophic baseline that's, you know, twice as bad as the individual ones, and then they show results that are only slightly worse. But our results were better. And they're not vastly better, you know, it's like 1% or 2%. But I suppose those results with the 1 hour were very impressive, weren't they? We had like 27 to 37. And that is a multilingual setting. So I think that really demonstrates the strengths of this approach, that you have so much leeway to use different data sets and combine things like that. So now the software that we've developed can in principle be made open source, and we've been proceeding according to that plan. We're not quite ready to release it yet because there's still a lot of packaging to be done. I'll just go through the various components that are in this framework and just show you how much there is. You need a bunch of scripts to build the baseline system. The standard resource management scripts don't really cut it. You need scripts to build the language models. You need scripts to improve the lexicon coverage. Well, in some cases you don't because the data set gives you, but in some cases you have a problem with that. Well, like in our case, we did need this because we had web data, and that doesn't have that, and GigaWord data, and that doesn't come with pronunciations. So we need a bunch of. Our whole setup is kind of weighted finite state transducer based, because that saves you the hassle of having to write a dynamic decoder. So we had to write these OpenFST based scripts to create our decoding graphs and our transcription kind of graphs. You make these little graphs for each sentence. And we have some scripts, and Aria developed for us some C++ code to do this in C for the numerator graphs, so that you don't have to load this vast transducer each time. It's just a practical issue. Then we have there's this whole kind of C++ based framework that's basically the decoder and a little trainer. This is so that you can decode in a nice software environment that you control. So we don't have to use a HDK decoder. And then, we have to obtain the UBM from the baseline HMM set. There's questions of clustering, retraining, stuff like that. Then there's a bunch of matrix vector code. All of this stuff is very heavy on matrix and vector manipulation. So we've wrapped kind of standard libraries in a nice way so that we can use them. There should be more people on that line. There's unit testing stuff. There's command line tool. Okay, this is an important part. There's the C++ class to do all of this stuff. So all of the equations that we didn't show would be in that part. Then there's command line tools to use that stuff, kind of analogs to HDKs, EREST, and the decoder, things like that. Then there's scripts to do the testing, to kind of call that stuff, put it on the queue, increase the number of substates, that kind of stuff. And of course, that ignores Rick's whole. Rick has his whole own structure, which I don't really see this as a waste of effort, because the result is that Rick now has his own setup that they control, they understand, and that they're going to do research on. Whereas the main setup is kind of based in Bruno. So now I would say this, but I'm quite optimistic about the future of this SGMM stuff. This relates a little bit to the question that Herb was asking, but all the standard stuff works. You don't have to do anything special. VTLA and constrained MLR, you can do discriminative training. Most things you don't even have to change the formulation. But you can do extra stuff because it has this extra structure in the model. You can mess around with the subspaces, you can share parameters on different levels. So it's a good thing. Now it is harder mathematically. There's more equations. There's, so that will tend to limit the speed of uptake. But I think that it's possible that people will start using it widely. That's certainly my hope. So I just want to summarize Nagendra's summary. I don't want to give the impression that this is the summary of everything Nagendra has done, because I'm not the right person to summarize that. But I think for me, the key result from Nagendra's stuff was that you only get like a 1% degradation from having hardly any lexicon at all. That if you're careful about combining these well-known approaches in a sensible way, you can do well without hardly any human annotation. I think that's an important result. And that's a useful tool when you're training on a new language or something. Now, we plan to include Nagendra scripts just like ours in the stuff that we release. We're going to work on all the packaging stuff. But so now for stuff that people can read, I have this long kind of tutorial document. It's at this location currently. And you can, if you want, maybe we can release the software before it's official. We'll have to talk to those guys about that. And I've given my email there simply because I respond promptly to email, and some of these guys don't. But I don't want to give the impression it's kind of my software, because these other guys did most of the work, especially the people in Brno. And we're going to publish about this, obviously. We don't know exactly how many papers we'll make out of it. And I get the impression that people plan to continue this research. I mean, obviously, I certainly do. But we have at least 2 setups that work, that are convenient to do research on this. So that's most of the work when you decide to do research on something, the having the setup. So I hope that we've reduced most of the barriers to entry, at least. So there we are. I don't know if we have time for a few seconds of discussion. Well, yeah.
So in some of the experiments that Pedro was doing, I'm trying to decide whether this business having subspace or substates,
Yeah.
how different it is from maybe having
Well, you mentioned something about duplicating the M's. I think that's a whole different thing, and that would be something equally interesting, but I think it's a different question.
do you think it's different? They're not
Yeah. Let's not keep people here, because we've already gone over time, and I'm sure, you know.
Maybe others have.
I think most of the questions already got asked.
Okay, thanks again.
Okay, quick.
You said that you have an approximate formula for updating the W.
Yeah, well, I mean, it's approximate only in a sense. It's exact in the sense that it's guaranteed to increase the auxiliary function. But it's approximate in the sense that you have to, it's not kind of a natural auxiliary function in the same way that it is in EM. You have to make a quadratic approximation to something and then make a step size and then say, did that increase the auxiliary function? But because you have the sufficient stats to evaluate whether or not you increase the auxiliary function. So it's exact in that sense.
Okay, so that it doesn't mean that it actually increases the likelihood.
No, it will always increase the likelihood.
Yeah, well, basically, you can see there is gradient, and you could do just gradient distance search for and go in the direction of gradient and increase the objective function. So I would say that it's approximate in the sense that we are trying to do second order optimization, and that is kind of approximate, but it always takes you in the correct direction. So that's mainly more question of the speed of convergence than whether it takes you to the right point.
I have a question about the lexical stuff. So essentially you have feedback loop, right? So you do the phonetic recognition, and so basically you add a bunch of transition stories. So so after you do the phonetic recognition, you said the likelihood goes up, but the accuracy actually doesn't make much sense. So I didn't quite get it. Why would the likelihood go up? Is it because you have a lot of pronunciations?
I think what happens is when we do the free phonetic recognition and align the words, obviously we don't pick up all the pronunciations and replace them, and that would be amounting to 5,000 replacements. What we do is we put some constraints that the word has to occur at least so many times. Now if we did replace all the 5,000 pronunciations, the likelihood will shoot way up, because now the audio likes what it sees in terms of phonetics, but that doesn't necessarily mean that it will generalize well. So we prune. We say that, okay, this is our threshold, and we are going to select only so many pronunciations, and we are going to give them back to the pool and train the system again. Now this loop of training the system again and choosing what tuning threshold, each experiment is about training a whole acoustic model and testing again. So it's a time-consuming proposition, and we started doing this. We got these numbers towards the very end of the workshop, so we have just not played around with the tuning thresholds.
Well, I don't know. What is it?
Okay,
Quick.
because this UK model seems to have somehow many and also small highly tight. So I would, and it's
Uh-huh.
up very quickly if you do this
On the wa-
space approach. So what do you think when it separates? So if you have something like 10 seconds to 100 hours
of a single
adaptation
speaker.
data.
Of
Adaptation data.
on a single. Oh, well, I don't know. Well, I mean, certainly map-like approaches would work better than normal, you would think, because you have so many fewer state-specific parameters, so it would be easy to estimate them. I mean, in general, it's more compact, so you would think these things would work better. Yeah. Okay. Thanks.